let's put this all together. We've talked about work, we've talked about heat. So the first law of thermodynamics is a change in energy of the system is equal to the heat transfer plus the work done. And it's really actually pretty simple when you think about this. If we've already said that the first law is conserved and that energy is either in the system or the surroundings, this is just a restatement of the fact that and if the energy of the system changes, it has to go into the system. It has to go into the surroundings, because the change in energy of the system, that's what delta E subscript system is. The change in energy of the systems is equal to the transfer of energy in and out of the system. That's pretty simple. If it's a state function, then the change, because it's conserved, then the change has to result from transfer in or transfer out. And the two ways of transferring energy in or out are either heat and work. So that's just really a restatement of this with a bunch of definitions put in. If it's going to change, it's got to transfer. What are the ways to transfer? Work and heat. Okay, so let's do some calculations. Let's use this a little bit more. Suppose that the heat transfer is equal to 0. What happens to the energy of the system here? Well, and here the setup is you've got a weight that's pressing gas down. You remove the stops and the gas goes up. And then we reach some final equilibrium. So what happens to the E system here? So let's start writing it down. This is where you could sit down and do it intuitively, but let's do the calculations just to see. So this is first law problem. So go way over there. Yes, okay. So no, I said go away. I want it all. Okay, there we go. Delta E is work plus Q. Actually, let me pause for a second. So remember I said that there's a sign convention there, right? So if you're using the other sign convention, then you get the delta E equals minus work plus Q. But and then if you use that convention for work, you have to use minus Q here. But if you do that, all your physical results will be exactly the same. So again, make sure you're using the right convention. This convention is nice because then you don't have to worry about where the sign is. It's just work plus heat. Okay, so delta equals Q plus W. And then the Q, we're just told Q is 0. Great. So the change in energy is simply equal to the work and change in is to the work. So it's just minus P delta V. And there's a weight pressing down, so it's definitely positive pressure, minus positive delta V. Delta V is positive, and so therefore this is a negative number. Delta E is negative, and therefore the energy change has, the energy is decreased. It had to give up some energy to lift the weight. So the energy is decreased because it had to give up energy to lift the weight. So here's another situation. We have blocks, so the piston can't move. At constant volume, this is in constant volume, the piston can't move. What is the change in energy equal to? Assuming we only have pressure and volume work, then that means that, let's write this out, delta E is heat plus work, which is minus P delta V. That's just, this here is plus work. And since there's no change in volume, it doesn't matter what the pressure is on the system. The change in energy is simply equal to the heat. Let's start putting things together. The following reaction results in a change of energy of minus 10 kilojoules. What are the heat and the work? Well, we're given enough information to calculate the work. So the work, let's change the format. The work is minus P dV. Great, that's simple. And it's the same pressure throughout. We'll assume it's constant. It's the same at the initial and the end. We'll assume it's not changing along the way. And that is equal to minus 1 atmosphere. And the change in volume is 20 liters. Sorry, let's be precise here. The change in volume is minus 20 liters. And so this results in 20-liter atmospheres. But let's just do the conversion here. 20-liter atmospheres, sorry, 1-liter atmosphere is 0.10125 kilojoules. So liter atmospheres cancel, and we get, so it's minus 20 liters, minus there, it's 2.025 kilojoules. Okay, so that's the work. What's Q? Well, delta E equals work plus Q, and so Q is going to be equal to delta E minus work, which is minus 10.0 kilojoules, minus 2.0 kilojoules equals minus 12 kilojoules. So we can calculate both the work and the heat, and you can see they add up to within significant digits. Obviously, I've rounded to get the final numbers, the significant digits. We get that the change in energy is just the work plus the heat. A way to rationalize this is we know the energy changed. The energy went down by minus 10 kilojoules. And the only way for that to happen is for work to be is for energy to be transferred. Well, the system was compressed, and so therefore more energy was put in. So if it loses energy, it has to lose not just the energy that was added by work, it has to lose the rest as well. So it has to lose more than 10 kilojoules because energy was added by work. So that is why the heat has to be greater. It's minus 12 to overcome the fact that the work done in order delta E equals minus, making these calculations quantitative.